Hello, and welcome to our next installment of Chem Honors Online. And in today's installment, we are going to be discussing strengths of acids and bases, the equilibrium constant Ka and Kb for acids and bases, and how to interpret them and how to start to make some use out of some calculations involving them. The first thing I want to do is draw your attention to chart H on the reference charts. In this chart, we have a list of many acids reacting. You can assume that there's H3O plus over these reactions to make, H2O to make H3O plus, or we can just say, all right, we're just making H plus, just to keep it nice and simple. We're going to make H plus. And on the right, we have the H plus and the conjugate base. And these acids are listed with the strongest acids on the top and decreasing acid strength as we go down. And as you can see on the left side of the chart, I have increasing acid strength, arrow pointing up towards the top. Now, at the top, what we're going to see is the strongest acids, and what I want to impress upon you is that the strength of the acid is going to increase as that HX bond or the HO bond. So whatever the hydrogen, the acidic hydrogen is bonded to, as that happens, as that HX bond or HO bond increases in polarity, in other words, a bigger dipole, a bigger delta plus, delta minus, more polar, bigger delta En, it becomes more ionic. And as it becomes more ionic, it becomes easier to break. If you recall, water is trying to pull those H's off. There's this tug of war between water and the conjugate base. And essentially, the stronger one is going to win. So as the bond gets more polar or weaker, so decreases in bond strength as well. And that's going to apply primarily to the HX, the halogens, on the right, the chlorine, bromine, iodine, and way down here, the fluorine. And we're going to have a little explanation about why fluorine is a weak acid, but in this case, why HF is a weak acid. But in this case, as the bond gets weaker, as the radius gets bigger, so as X gets larger, then we're going to get a stronger acid because it's going to be a weaker bond. So strongest acids have the weakest HX bonds. And it's going to be the easiest for those, for water or some other base to pull that H off. And the conjugate base of a strong acid, and this is going to be important later on when we talk about weak acids and bases, has literally no tendency to attract a proton. So even though we call it a base, it's an extremely weak base. And so for that reason, the strong acids on the chart are written with a single directional arrow pointing to the right. There's no equilibrium going on. So what are those acids? There are 6 strong acids that you need to know about. You'll always have this chart, so they're always going to be at the top of this chart. Those 6 strong acids that dissociate 100%, that was the definition we used before of strong acids. So 100% dissociation, remember lots of ions, are all of the acids at the top that have a large Ka, or large acid equilibrium constant. Now we'll come back and talk more about what the Ka means in a few minutes. Now sometimes we do include, and it's not on the chart, but sometimes we do include HClO3 as a 7th strong acid. It's got about the strength as an acid of H3O plus, so it's about in there, and there'll never be an ambiguity. You'll know if it's supposed to be a stronger acid than the one that it's going to be paired with, as we're going to see later on. So when you're looking at this chart, the thing to notice is that all 6 or 7 if you want, of those strong acids are above hydronium. They're above the H3O plus. So here's our H3O plus. Now it has a Ka of 1 because essentially the concentration of H2O, the concentration, of H plus, H2O is a liquid. The concentration of H plus is the same as the concentration of H3O plus. So products over reactants equals 1. And the idea behind H3O plus is that it's the strongest acid that can remain undissociated. In other words, it doesn't lose a proton in water. All of the other acids above it are going to lose a proton in water, and H3O plus is going to lose a proton in water, and then it's going to, things down below it, we're going to start to see not losing protons in water as much. On the other end of the scale is the strong bases. Now, there's a couple of ways to think about strong bases. The first way is to look at compounds that have hydroxide in them. And if they're soluble hydroxide compounds, and those are going to be compounds of the alkali metals, and in addition to the alkali metals, calcium 2 plus, strontium 2 plus, and barium 2 plus. Those are the alkaline earth metals. Well, those are the lower alkaline earth metals. So hydroxide compounds of those guys, they form a B for a base on the periodic table. And so if we look at lithium, sodium, potassium, rubidium, cesium, next to potassium is calcium, strontium, and barium. You can kind of see the outline of a B, lowercase b, on the periodic table. That's going to help us to understand the six strong, the strong ionic or inorganic bases. Now, there's also a couple of really strong bases down below. So just like H3O plus was a cutoff for acids, hydroxide right here is going to be a cutoff for the bases. And the two reactions down below that hydroxide, now remember, that's going to be hydroxide acting as a base going in the reverse direction. These two guys down here, on the right side, these are the bases, O2 minus, and I kind of drew over that, but that's a 2 negative charge on the oxide. And this guy, NH2 with a negative charge. These guys are extremely strong bases. And because of the extremes, let me rewrite strong so it looks a little bit easier, a little better, extra strong as bases. And these, remember, over here, these are the Kas, which means that to the right, there's almost no products formed. And in fact, in these cases, the reaction is going to be completely to the left. So those guys are below OH minus, and OH minus is the strongest base that remains unionized in solution. Okay, you can stay there. Otherwise, the O2 minus is going to form hydroxide, and H2 minus is going to form ammonia. In between is where a lot of our interesting chemistry is taking place. In between hydroxide and let's use green for this. In between hydroxide at the bottom and coming up to sulfurous acid up at the top there, and hopefully you can remember some of those acid names after yesterday's or the previous homework. We have weak acids and weak bases. So this is a combination of weak acids and weak bases. Now, the conjugate base of a weak acid is itself a weak base. It's not going to be a strong base. The conjugate base of a conjugate acid of a weak base is going to be a weak acid, not a strong acid. When I'm talking about conjugates of strong acids, those are things that are essentially not basic. the conjugate acids of strong bases are essentially not acids. They just don't have any acidic or basic properties. So a strong acid is going to have a weaker, or a stronger weak acid is going to have a weaker conjugate base. So up near the top, we've got the sulfurous acid. For instance, sulfurous acid, if we were to think about the conjugate base, this reaction is not going to go very far to the left if we put in some sulfurous acid. So this is going to be a weak base. Likewise, the weaker the acid down near the bottom, the HS ion down here, the weaker acid has a stronger conjugate base. And so S2 minus is going to be pretty strong as a conjugate base. And we're going to get a lot of HS minus formation if we were to put S minus into solution. In reactions, we're going to have a strong acid, a strong base, a weak acid, and a weak base. And the strongest acid is going to do what it's supposed to do. The strongest acid will lose its H plus, and the strongest base will gain an H plus. Now remember, when we talked about the Bronsted models of acids and bases, we said there's an acid and a base in the reactants, there's an acid and a base in the products. And because of the way this table works, and because of the fact that when you pair two things together, if you have something that's a stronger acid on one side, it's going to be a weaker base on the other side. And so it always turns out that the strongest pair is always on the same side of the equation. Now, what you need to do, the easiest way to do this is to compare acid strength. And that's going to help us to determine whether the reaction, the equilibrium that's determined by a reaction between an acid and a base, is going to lie to the left or to the right, whether it's going to be product favored or reactant favored. So when we look at this reaction, if we look at our acids, we have nitrous acid on one side, and we have H3O plus. That's our acid and our conjugate acid. So let's circle those up above. We've got nitrous acid here and H3O plus, I can just barely fit it in, up here. And so the nitrous acid is the weaker acid. Between the two of them, the nitrous acid is a weaker acid. It's lower on the chart. It also has a lower Ka. And so that's going to help us to identify the weaker acids. Conversely, now look at the chart. I have on the right increasing strength as a base. That means that the NO2 minus, the nitrite ion, is going to be a stronger base. Well, if we look at it that way, H2O has to be a weaker base because H2O is the base on the left side. And the H3O plus has to be the stronger acid. And you can see that in the table because it's up higher. So the conjugate base of the weaker acid has to be the stronger base because we're just comparing two things. That has to be the case. The conjugate base of the stronger acid is the weaker base. And the stronger acid and stronger base must be on the same side. And if you look at this reaction, they are both on the same side. Oh, I should have said this is an acid. So since the stronger acid and the stronger base in this reaction, this is always going to be the case, are on the product side, the equilibrium is pushed to the left. Remember, we said the stronger acid is going to want to give up its proton. The stronger acid is going to do what acids do naturally, give up protons. The stronger base is going to do what it does naturally, accept a proton. And so in solution, this is going to force this reaction to go to the left, and the equilibrium is going to lie with higher concentrations of the nitrous acid and the water. And so The other way of thinking about that is that the H3O plus has the greater tendency to donate the proton. It's a stronger acid. And so it's going to react and it's going to be present. So the H3O plus is going to be less concentrated. And so this equilibrium constant for this reaction would lie to the left. The equilibrium will lie to the left. Now, I'm never going to have you calculate an equilibrium constant for these reactions. It gets a little complicated. Not that complicated, but I don't want to get into it for right now. All right, so we've got this reaction identified as what direction the equilibrium lies. So it's a reactant-favored equilibrium. In the next example, let's see if you can do this before I go through this with you. So why don't you pause the video for a moment and go through, identify the stronger acid, the stronger base, the weaker acid, the weaker base. Again, if you can identify just the stronger acid, that's going to be all you need, but just do it for to prove to yourself that identifying all four of those is going to be consistent. So pause the video and then start it up again when you're ready. So here we are. I hope you have paused the video like I suggested. Now let's take a look at the acids. What are our two acids in this reaction? Our two acids are HF on the left and ammonium on the right. So let's find those guys on our chart. Here's ammonium, fairly low, and I had already circled HF before up above. So according to this chart, HF has a higher Ka, and so it is the stronger acid. Let's label the HF as the stronger acid. That means NH3, which is on the same side of the HF, must be the stronger base. Since the NH4 plus is the weaker acid, its conjugate base, the weaker acid, its conjugate base, the NH3, must be stronger. So HF, hydrofluoric acid, has a larger tendency to donate protons. Ammonia has a greater tendency to gain a proton. So we're going to take that proton and let's go ahead and do the transfer, show the transfer, proton from the HF to the NH3. And this equilibrium is going to lie to the right. And this is going to be a product-favored equilibrium. And it would be one that if we did calculate the equilibrium constant would be greater than 1. So how are we going to make use numerically of these equilibrium constants? Well, we've already seen some equilibrium in action. And so let's take a look on the back how to apply these equilibrium constants that we see for the weak acids. And we'll also throw a weak base in there as well, which is not on here, but I'll always tell you, and you can always see if something's a weak acid or a weak base. So for weak acids and weak bases, we have established the equilibrium constants, the acid Ka and base Kb, dissociation or ionization constant. So Ka is going to describe the ionization constant of an acid in water. It has to be that acid in water. So the reactants always have to be that acid in water. Here we have, in this reaction, we have acetic acid and water. And the Ka expression is going to be, like we saw before, products over reactants, the concentration of the acetate ion times the hydronium ion divided by, now don't forget, water is a liquid, so don't include that water in the acid dissociation constant. But even though the acetic acid doesn't break up, it is still aqueous. It's a polar covalent compound, so it does dissolve in water. And so that has a concentration that we need to take into account. Undissociated, but still dissolved. And so what I'm going to do is give you some ICE tables. We saw these before. ICE standing for an initial concentration, a change, and an equilibrium concentration. And I'm going to give you some of the values to fill in. You're going to use stoichiometry to fill in the rest of the values, and then you're going to use those values that you've figured out to determine what the equilibrium constant, what the acid Ka value is for this particular reaction. So here we have a solution that has an initial concentration of acetic acid as 1 molar. And I've got that filled in under our I. So that's right here, our initial concentration of the acetic acid. And I tell you that at equilibrium, the concentration of the H3O plus is 0.0040 molar. I wish that M had been on previous line, but that's okay. Now, how did we get here? Initially, when we say initially, I mean, suppose that we could stop time, put that 1 molar acetic acid into solution. At that point where time is stopped, we have no acetate ion, so that's 0 molar. By the way, these are always in molar, so sometimes I might leave those off, leave the molar off. And the H3O plus is essentially 0 molar. Now, we'll see that in the next lesson, that's not 100% true, but generally we can disregard what initial concentration of the H3O plus is there. Our change has to get us from H3O plus of 0 to an H3O plus concentration of 0.0040 molar. So can you see that in order to do that, we've had to add 0.0040 molar of H3O plus to our solution. But we did that by doing this reaction. We didn't just throw H3O plus in, we threw acetic acid in. And so that acetic acid associated, and this is a 1-to-1 to 1-to-1 ratio. So every H3O plus that we made, we must have made 1 acetate ion. And so the acetate ion concentration also goes up by 0.0040 molar. So that gets us with a final concentration of, you guessed it, 0.0040 molar H3O plus. Meanwhile, in order to form those concentrations, we had to use up each one of those acetates and H3O pluses came from a single acetic acid, and so we're going to use up 0.0040 molar. Now, these guys are pretty nice reactions because the stoichiometry is always going to be 1-to-1 to 1-to-1, so you don't have to worry about what's limiting, things like that, limiting reactants. It just goes. And so that's going to leave us with 0.996 molar concentration of acetic acid at equilibrium. So as I said, initially we had those concentrations. Our change was to increase the two concentrations by 0.004 molar and to consume 0.004 molar of the acetic acid. And so at the equilibrium, we have that combined I plus C, which I've already done for you up there. I've combined I plus C. In the case of the acetic acid, the C was negative. And so we can plug these numbers into our expression that we determined up above, and we get 0.0040 times 0.0040 divided by 0.996. And when you do this math, we get 1.6 times 10 to the negative 5. So that would be our equilibrium constant. Now, if you look back on chart H, you will find acetic acid with a value of 1.8 times 10 to the minus 5 for its Ka. The reason for the difference is just due to some rounding errors in the way we calculate some of the way we put some of these concentrations in. So don't worry that there's a slight difference there. You're close to what it should be, and that's what we're looking for here. So anytime I give you a concentration of the initial concentration of the acid, I will give you the concentration of the H3O plus, and you can fill in the ice table and determine the Ka. For Kb, it's going to be a similar thing, except for now we have the reaction of a base, ionization of a base in H2O plus. Now, this is definitely an ionization. This is not a dissociation. Acids are dissociations as well as ionization. In this case, the water is acting as an acid. It's going to give as an acid. It's going to give its proton to the I believe that's hydrazine. Yep, the hydrazine, which is the base. And so the Kb is going to take the aqueous. Oh, there's a little typo there. There should be an aqueous on the hydroxide. Sorry about that. Squeeze that aqueous into there. So the Kb is going to be, and there should be an aqueous down here. Boy, I wasn't very good, was I? Kb is going to be the concentration of the N2H5 plus times the concentration of the hydroxide divided by, again, the hydrazine is a polar covalent molecule, so it does dissolve in water. It just doesn't 100% ionize. In fact, it has a very low ionization percentage. So I'm going to give you the same sorts of numbers here, except that's the initial concentration of the base, the initial concentration of the hydroxide. And as we did up above on the bottom of the previous page, let's pause for a moment with these numbers and see if you can figure out what the Kb is for hydrazine. Okay, so I hope you pause it. Let's go and take a look at what our numbers are going to tell us. Initially, our concentrations of the hydrazine and the hydroxide are 0 molar and 0 molar. To get to 0.00123 molar, I have to subtract 0.00123 molar from the hydrazine. I have to add there's a molar there, 0.00123 molar to the, what would you call that, hydrazinium? Let's call it hydrazinium. You're never going to have to know what those names are. And plus 0.00123 for the hydroxide molar. And so we're going to end up with, I'm going to write a few more sig figs than I should here just to get that out there, 0.49877. Now, if I did round that to the third decimal point, which I should do for rounding, that's going to make it 0.499. which we can use in the calculations, or we can use 0.49877. The hydrazinium, 0.00, put a molar there, 123 molar for the hydrazinium. And now the Kb, we have the Kb expression up above. And so let's plug in some numbers. We have 0.00123 molar, but we have that times itself. So let's just put a squared on there. That's perfectly fine for you to do because we have the two there then multiplied together. And we're going to divide by 0.49877. So we're only going to take this out to 3 significant figures anyway. And what that's going to give us is a value of 3.03 times 10 to the minus 6. And that's what you would expect for a relatively weak base. All right, so this is strengths of acids and bases. If you have any questions, please don't hesitate to ask. Otherwise, you've got the homework and you can get started on that. Have a great day, and we'll see you in the next class. Take care.